Okay, hello everyone. It's February 19, Friday today. Let's start our day 13, our lecture. So I recall you have your exam just in a week from now, right? February 26, online. So please take it seriously. Please spend the time left, the week left by being preparing to this exam. That's serious and that's important. Your homework is due, your homework 3 is due Wednesday. And we will have help sessions on Monday and Tuesday for this homework, TA help session, like usual. And also I will give my help session on 5 o'clock on Wednesday. And again, I will be ready to answer your questions. So please take all these resources, but key point practice property tables, spend at least 6 hours on the property tables and homework 3. It's really important. Now, last night, if you remember, I sent you some what I call supplementary materials for the exam. 3 items I sent to you. And let me share my screen and recall it. So what I sent to you were the following. I sent you a couple of things. I sent you so-called topical overview. So what you should do with this topical overview. So please, you will go through all these lines and read them. And you should be ready to talk about 30 seconds or minute for each of these items. If you have nothing to say about them, it means that you don't know this topic and it's time for you to read about it. From textbook, from my lectures, from recording of my lectures, but that it is. If you have something to say for a minute, okay, so you most likely know the topic. It's topical overview. I send you what else? I send you summary slides. These summary slides just like, well, this summary slide just like really essence of what has been in 3 chapters. Just brief summary. Now, please don't get misled and don't overamplify the material. The worst scenario that may happen is when you will prepare for your exam based on my summary slides and nothing else. Then you fail, believe me. If you ask me the morning before exam, where is my property table, I will tell you where they are, but you fail. You will not have time to complete it. You should do everything else. You should practice a lot. The summary slides you see I sent to you, it's your last source for repetition. Like on Thursday evening or Friday morning, it's good to go through them to repeat. It's not to replace your textbook and my lectures, believe me. Now, well, if you are not get prepared, anyway, if you need something, well, it's still some source. If you don't have time to read your book last night before the exam, okay, you still have the slides to go and try to get some reasonable score. That's my help. But please don't overamplify it. Your key point, do your homeworks, do it yourself, and then it will be okay. If you understand when I'm solving problem on the screen, on the computer, or if I understand my solution of your homework, is great. It's better than if you don't understand it, but it still does not guarantee that you solve this at your exam. You should solve after you see the solution. You should close it and solve it yourself from scratch. Only in this way, I can guarantee that you will do it yourself at your exam. Okay. Now, another thing I send you, this is what you call a list of equations. So basically, first concept is tentative. So basically, you are expected to write your exam without any notes, without any, you should memorize everything. But I know it's difficult, so we allow to give you some list of equations for up to 1 page. Which will be, so your page of equation will be included in your exam. And it may be different from this. What I send you here, it's tentative, okay? It's tentative, but it's fruitful for you to take a look to make sure you know it. And please, again, don't blame later that you may say, I was preparing based on this list of equations, you gave something else. Yes, I may give you something else. Yes, your knowledge should not be limited by summary slides, list of equations, and topical overview. Everything from chapter 1 to 3 can be there, believe me. I am here to help you, but I am not replacing the whole exam. So please realize. Okay, does it make sense? Any question? Now, Today we are completing this chapter. We almost completed chapter 3, and you are ready to do all the homework except the last problem. And today we will be talking about ideal gas. And I told you in advance before we start. So what is conceptual mistakes the students do? Because ideal gas is the last topic of this chapter, and then you will have exam, people will use ideal gas law anytime, anywhere. You apply ideal gas law for liquids, for solids, for ice, for whatever. So please realize, you should use tables. Tables is your major source. Ideal gas happens very seldom. Most likely, your substance is not ideal gas. And if it's ideal gas, it should be justified. Does it make sense? So don't use ideal gas unless you have unless you have some understanding why you should use it. Do you agree? Do you understand this? Okay, great. So, questions? Yes, exam may require drawing of PV and TV diagrams. It may require. Yes, it may require. And also, again, I told you, identification of phase and ability to identify yourself on PV and TV diagram, the state on PV, not yourself, state PV and TV diagram. It's a major assignment you may have from chapter 3, right? That's most important. So let's go back to chapter part C of the slides I sent you yesterday. Or you see it on my screen, and that's actually what we're talking about. And that's we will talk about properties of ideal gas, right? That's our objectives, to understand how to deal with to apply ideal gas equation, and also to distinguish ideal from non-ideal gas, which is even more important. Because most likely, I think you know ideal gas equation, most of you know it. But to distinguish ideal from non-ideal, it's something new for many of you. So let's do it. So let me ask you, so what is ideal gas? How do you feel it? Please write down or whatever. So what is ideal gas? What is ideal gas? Yeah, you may know it's a model, right? There is no ideal gas in reality, but sometimes for some situations, some gases, this is a good approach that we use. No, it's not gas at saturated point. It's not gas at saturated point. It's something different. Ideal gas. Yes, first of all, you're right that it should be superheated. But yes, ideal gas is superheated because it's gas, right? Liquid mixture, solid liquid, saturated mixture cannot be ideal gas. But not all superheated vapors are gases, right? So molecules don't attract or build charge. Yes, that's great. That's true. And anything else? Yeah, one person is very active and it's great, and he or she is getting a lot of bonuses. But I want everyone to, not everyone, but at least me, to spread bonuses between different people. Okay. No, it's not standard temperature and pressure. Okay, so let me do like this. So there are ideal gas. It's more ideal gas model has two assumptions, two approaches that we use. Our approaches are the following. Our assumptions are the following. We say that particles don't interact and the particles don't have size. Okay? What does it mean that particles don't have size? They have zero size. What is it? Do particles have zero size in reality? No. They have size. So when can you neglect the size of an object? When you can neglect your size? When it's small as compared to something, right? As compared to what? So in gas, what is it? What does it mean that particles don't have size? It means that particle size is extremely small as compared to mean free path, as compared to the distance a particle propagates until the particle interact with other particle, right? So particles are very rarefied, right? So particle size is negligible as compared to the distance between the particles. So it should be very rarefied. And if it's rarefied, yes, another assumption that we use that particles don't interact. So what does it mean that they don't interact? In practice, they do interact. but it means that we talk about like free particles. It means, you remember what we know about particles, that particles have kinetic energy, which is temperature. But also there is collective motion of particles in fluids, in gases and liquids, right? So particle is free, it means that its kinetic energy should be much, much larger than what? Than potential energy of interaction with other particles. So how we call this potential and kinetic energy of particles? Remember, we call it latent and sensible. So what it means? It means that for ideal gas, your sensible energy is dominating over latent energy. Like imagine you have a crowd, and in this crowd you run very fast, then nobody can catch you. Then you are like a free, right? So that it is. So, and that means that particles should be, definitely to have this, particles should be really rarefied. You should have big distance between particles, because in a liquid they are very close, then really you cannot go very fast. This is opposite limit. So that it is. And based on this, you will have from here that if sensible energy dominate over latent energy, what does it mean for us? It means that temperature, it will be your only parameter. So your internal energy, your enthalpy, they will depend on temperature. And temperature here, you see on the screen, it should be in Kelvin, right? Because it's kinetic energy of particles. It's from absolute zero. It's not Celsius that can be negative. Temperature should be in Kelvin. So otherwise, what it is? Like remember, we talk about fluids, which are liquids and solids. Sorry, liquids and gases, I'm sorry, liquids and gases. And what is the difference? Then in liquids, particles are close to each other, they interact. In gases, they are more free, that's why the gas occupies the entire volume allowed, right? So ideal gas is like limit of this gas. It's ideal limit of a rarefied gas. So particles occupy everything, they don't interact, it's absolutely free. And opposite limit is what? Opposite limit is incompressible liquid, which is already compressed in such a manner that you cannot compress it anymore. It's there. So that it is. Now, let me explain you something. You should realize at this point. Remember, there is classical statement from the literature, from Leo Tolstoy, that all happy families are happy in the same manner. All unhappy families, they have their own disadvantages. What I mean? Like happy family is something like saint family, something ideal. It's not your family, but something you want to resemble. And if you resemble it, that you cannot distinguish anything. But we all have our own characteristics, which are our disadvantages, which makes us different. So what I mean? I mean that all ideal gases are identical, provided they're ideal. While if you distinguish gases, it means that you find some non-ideality, you see how they're different. What I say? Very silly question, but I will ask you. So you are students, right? How, and what about ideal? What is the difference between ideal gas of students and ideal gas of rabbits, and ideal gas of elephants, and ideal gas of planets? Okay, you are students, right? So let me ask you, how do you know that you are a student? Maybe you are a rabbit. Sorry for comparison. Maybe not, no, but let's say, maybe you are a rabbit. How do you know that you're a student? I believe because you interact with other students rather than rabbits, right? I believe you see your friends, and sometimes you look at a mirror and you see, okay, if you look at the mirror and you look at your friend, and if you look at the rabbit, you will say, I'm rather a student, right? But imagine you are the only item in vacuum. You have zero size, and you never interact with anybody. Will you then know that you are a student or rabbit? Maybe you will not know. That is. So, as long as particles don't interact, they don't have size, they're absolutely different. And all ideal gas, and that is our point. And next we will derive equations to quantify ideal gases. And you will see that eventually we scale them in such a manner that all ideal gases will come into one equation and one curve, while non-ideality will show their differences. Okay, now, so we will come to ideal gas equation now. So basically what we know from it comes from what? There is classical Boyle's law, which says that if your temperature is fixed, your pressure is inversely proportional to volume, which it should be. The more particles you put, then the higher the pressure. And there is Charles' law, which says that volume is proportional to temperature at constant pressure. I believe you also know this. True? Then, from these two equations, if you multiply first and second, you will simply come that PV, what is PV? It should be proportional to temperature, right? And that is ideal gas law. PV is proportional to temperature. So what is your, if it's proportional, so what is your proportionality coefficient? So I will write like this. PV is CT. Again, remember, T is here in Kelvin. Well, it can be in Rankine, but it should be from absolute zero, right? Because it's kinetic energy of particles. So what this coefficient C is? How to get it? Well, people got it experimentally, but you may realize that it should be proportional to number of particles you have in your system, right? So basically, we can write it like this. It's N by T, and the coefficient's what we call Boltzmann constant. This coefficient is what we call Boltzmann constant, okay? So what is Boltzmann? Because it was Boltzmann who calculated this, and that's Boltzmann constant. Now, what is it? Boltzmann constant is very small value, right? It's 10 to the minus 23 joule per Kelvin, and it should be. Why it's very small? Because N is very big. How many particles do I have in this room, for instance? It will be 10 to the 27, 10 to the 26, something like this. So it's a very big number. And that's why Boltzmann constant is small. And that's a good equation, but typically people don't like to deal with big values and small values, right? Why should I operate with billions of billions of billions of particles, right? 10 to 27 is billion of billion of billion. So people actually express it this formula in a different manner sometimes. People express it in terms of moles. So there is a concept of mole. Mole is reasonable amount of matter we deal with. So what is 1 mole? Do you know? Do you remember from chemistry, from other classes? So by definition, 1 mole is what we call Avogadro or Avogadro. I will use Avogadro, French name, Avogadro number of particles, of items. So Avogadro number is very big number. It's 60222 by 10 to the 23. It's almost 10 to the power 24 items. It's Avogadro number. So let's realize 1 mole of hydrogen, it's hydrogen mole, it's Avogadro number of hydrogen. 1 mole of water, it's Avogadro number of water molecules. 1 mole of students, it's Avogadro number of students. I'm not joking, it's definition. If you have this amount of students in the universe, it will be a mole of students. 1 mole of planets, it will be Avogadro number of planets. 1 mole of galaxies, it will be Avogadro number of galaxies. Does it make sense? Why is this number not different? Because it's convenient to use, because 1 mole of hydrogen weight 1 gram, okay? 1 mole of carbon weight 12 gram, and so on. So then, what people typically write, we can rewrite equation like this. Instead of N, you express what is N. It will be Avogadro number multiplied by number of moles. So here N is a number of moles. We call it also stoichiometric coefficient sometimes. And N Avogadro is for 1 mole. So here you see how many moles you have, and here's Boltzmann constant and temperature. What's next? So then I can combine these 2 items. What do you see here? I have 2 items. I have very big Avogadro number, and I have very small this number, right? So I can combine them. I can combine them together. If I multiply Avogadro number by Boltzmann constant, I will arrive to what we call universal gas constant. Its universal value, which is 8314 in joule per mole Kelvin in C units, for instance, is the universal value, like whatever it is, like number E, number pi, and so on. Its universal gas constant from the table. And then I can express my equations like N multiplied by universal gas constant by T, right? What else I can do? That's actually my equation. But also very often people don't want to deal with moles. They prefer to deal with mass, right? Mass and volume. So what I can do? If I have number of moles here, I can rewrite it like this. I can take my total mass, and if I divide by molar mass, then I will have N here number of moles, right? So please realize what is molar mass. It's mass of 1 mole, and you can get it from your table. Like I say, 1 mole of mass, molar mass of hydrogen, it's 1 gram. Molar mass of oxygen, it's 32 gram. Molecular oxygen. Molar mass of water, it's 18 gram. Everybody knows this from other classes. Everybody remembers this. So then I write like this. And then, but why I write like this? Then I can actually rewrite my equation as follows. And then I have 2 items here. So instead of writing like this, I can take a fraction R universal over M and replace it by another value. So I introduce something that we call a specific gas constant, okay? Specific gas constant. It's tabulated. It's specific gas constant. And then here is my equation. So please remember, don't confuse universal gas constant and specific gas constant. Universal gas constant, it's this constant. Specific is when you take it divided by molar mass. So realize specific gas constant for hydrogen, it's universal divided by molar mass of hydrogen. Specific gas constant for uranium, it will be 8.314 divided by molar mass of uranium. Specific gas constant for students, it will be this constant divided by molar mass of student or molar mass of elements. I'm not joking, it's true. Another point, the students don't behave like ideal gas most of the time, but that's by definition. Do you understand this? So now my equation becomes like this, and that's typical form that you see. PV is equal to mRT, and I recall R is specific gas constant now, not universal, and T is temperature. And what I can do? Now I can multiply or divide both sides by volume or mass. For instance, if I divide both sides by volume, this will be my equation. It's M over V RT, it's rho RT. And that's mostly you see in physics. But in this class, you know, we don't prefer density, we prefer opposite to density quantity, which is specific volume, because it will behave similarly to specific internal energy, enthalpy, and so on. So basically here it is. And that will be your equation. So that's what we use typically, that's how we write it down. So that will be typically your equations that you will use. Okay? Like this. PV is equal to RT. So that's also all equations I wrote above the ideal gas law equations, but this is most common equations that people use, and that's what we use in this class. So please, I think all of you have seen this equation before and know about it a little bit, but please remember what values you use here, that don't confuse. That P is pressure, V is specific volume, inverse density, it's not total volume, it's specific volume, it's meter cube per kilogram. R is specific gas constant, okay? It's not universal, it's specific gas constant, which will be measured in joule per mole, joule per kilogram Kelvin, right? Because you divided not by mole here, and temperature is in Kelvin here, okay? Any question about this? Anybody knows this equation? So that's equation we are using for ideal gas. If you employ ideal gas equation, we use it. And here you remember that here universal gas constant you may, in different units we use in kilojoule, in kilojoule per kilogram Kelvin, in different units you may have it. And also please realize that specific gas constant is different. Specific gas constant is universal divided by molar mass. So, and I want you to refer you to our property tables. The property table here, table 1, it's just your very first table A1. If you see here, here are all the substances, and for all of them you see here is a molar mass in kilojoule per kilogram, and here is a gas specific gas constant R. And you may easily check if you multiply this by this, multiply this by this, multiply left column by right column, you will arrive to 8.314. You will arrive to universal gas constant. Please don't confuse specific and universal gas constant. Remember it. Okay, that's actually stated here. Any question at this point? Okay. Now, then, our next question will be, okay, so now you know what is ideal gas. Where you can use ideal gas law and where not. What is ideal gas, what is not ideal. when this approach can be used. And that's what we are going to do next. For instance, is water vapor an ideal gas? And the answer is sometimes, but even vapor is not always ideal gas. Here, actually, on this screen, you see classical our TV diagram, and you see this our saturated liquid line, saturated vapor line, saturated mixture between them. It's compressed liquid and superheated vapor here. And so you will see here is ideal gas. So definitely, when you have lower pressure, when you have very rarefied flow, you do have ideal gas. For water, it's typically less than 10 kilopascals. So definitely when your pressure tends to zero, when you tend to vacuum, you will eventually arrive to ideal gas. But otherwise, not the same. That's not always the case. And you may see here another point, that ideal gas is something which is far away from critical point. Supercritical condition is definitely not ideal. So what you see here, do you see now that it will ideal gas, like not ideal gas, that whether it's ideal gas or not will depend how far you are from critical point. From critical point is here, remember, right? Critical point is here. So, and how far you are from it, it will depend on if it's ideal gas or not. Okay? So what can we do? How we measure it? Now, please listen to me. It's something important, the most important part of this lecture. So, to clarify if it's a is we introduce a concept of compressibility factor. So, what is compressibility factor? By definition, we say that for any substance, I can say that my compressibility factor Z is PV over RT. So, what is it? Why we introduce it like this? So, but definitely, if Z is equal to 1, what does it mean? If Z is equal to 1, that you will have that PV is equal to RT and it's ideal gas by default. But generally speaking, you arrive to not like this. You will have something like this. So you will have that PV is equal to ZRT. So you will have some coefficient here, right? And actually also what happens here? You may also see that Z's will be what? Because it's V over this value. So if it's ideal gas, what the value that I crossed is what? It's ideal gas, right? So basically Z is actual volume divided by volume, how it would be if it was ideal, right? So this is a measure how you deviate from ideal gas. Do you understand? Obviously, if pressure tends to zero, your real gas tends to zero. Your real gas, the gas I mean, tends to ideal gas. But otherwise, it may not be the case. So for absolutely ideal gas, Z is 1, while in reality, Z may be different. So what is Z? It's actually Z is actual volume divided by ideal volume. Do you understand? Now we arrive to nice criteria. We say that, well, it depends on the book, but typically we say, if Z is in between 95% and 100%, so that is from O95, right? Or I say that if it's from O95, so if it's like this, then because we know that in reality it's never is one, right? We are physicists, we are engineers, you know that nature is not ideal. But if you have this condition, if Z is from 95% to 100, then we say that it can be treated as ideal gas. Okay? Well, it depends on book. In some books you see 97%. Let's say 95 in this class. And I will not confuse you much, so I will not give you problems when Z is really close to 100. I will give you Z either like 99% or 20% or 80%. So you will see the difference. So that is the definition. So we look for Z and say, if Z is from 95% to 100%, then it's ideal gas. Otherwise, this is not ideal gas and you cannot use ideal gas law. Does it make sense? Please ask me something. Do you agree with me? Does it make sense for you? Okay, great. Now, There is a good point. What happens if z is like, what happens if z exceeds 1? What if z is like, say, 1 or 1? Well, it's a tricky question which I really would try to avoid and don't consider. I will tell you why. Like mathematically, this is a small error. Mathematically, it's a small error, so you can count it. But what physically means that compressibility factor is larger than 1. Compressibility is larger than 1. What is ideal gas? And I will show it again. You will see when you come to van der Waals gas, real gases. So remember ideal gas approach. Particles have 0 size and they don't interact, right? What does it mean that 0 is a little bit less than 1, like 95%? It means that particles have very, very small size, okay? And they weakly interact. And the less z is, the larger the particles are, the more volume they occupy, and the stronger they interact. But what would mean that z is larger than 1? It would mean that particles have negative size, or particles not contract instead of attraction, which is really strange, which cannot happen physically. So let's say that z should be always less than 1, but this is your criteria when it happens, right? If it's ideal or not. Okay, everybody understands this? Now, the next question will be, okay, so the next question will be, so how to find z? Okay, it's good if you know pressure and temperature, then you can calculate it from here. But there is another way to calculate, and that's what I will be talking about. And there is table A15, what we call Nelson-Obert chart, which helps you to solve this. And now I recall, please look at my screen, and I will tell you again some very important philosophy here. So let's see. Let's see, guys. So this is TV diagram, arbitrary TV diagram. We don't know what substance we talk about. And we discussed that we have ideal gas here. Why we have ideal gas here? Because it's rarefied. And we have ideal gas here because it's very, very superheated. It's far from superheated line. But definitely it's not ideal here. Correct? So to be ideal, please listen to me. To be ideal, you should be far away from critical point. Right? So if I'm here, it's not ideal gas, right? Right. So if I'm here, then Z is definitely far from unity. But if I go from here to here, or to here, that my Z will change and will tend to approach unity. Do you agree? Yes, I believe so. So then do you agree at this point? Do you agree with me? Then Z, factor Z, should depend on this point. Do you agree that Z should be function of what? It should be some function of critical pressure and critical temperature. Agree? And also should be depend on your particular situation, so on your temperature and your pressure. Do you agree with this? Well, I didn't prove it, but I like explain it's my philosophy here, right? But then remember what I told. Remember what I told. I told you that all happy families are happy in the same manner. So if you use ideal gas of propane or ideal gas of methane, or I'm joking now, but ideal gas of elephants or ideal gas of students, they are identical. So it should be the scaling which allows you to do it. So in reality from here, I will say that my Z depends on scaled values. My Z depends on my temperature divided by critical temperature. And my pressure divided by critical pressure. Please tell me if you understand what I'm talking about. I know it's not rigorous provement yet, it's just my guess, but I will prove it later. But do you understand this? What I say here, that Z should depend. So what these scaling values mean? They show how far you are from this point, correct? Correct. Great. So in reality, it means the following, that I introduce. Now let me do the following. So you know critical pressure and temperature. I will get it from my tables. I have my tables. So I introduced the concept of reduced pressure and reduced temperature. So what is this? It's scaled value. It does not have dimension. It's a number. And it's I take my pressure for any substance. I take my pressure and divide it by critical pressure. I take my temperature, okay, and divide it by critical temperature. Okay, it's scaled value. And then it will happen that my Z should be a function of these reduced values. Reduced temperature and reduced pressure. Correct? True? True. Okay, so that will be my strategy. And now, how to see how it looks like. And now, yeah, what I told you that it's for such a function, it was like you say, how do you know this? But there are experimental findings, and what you see here. If you see on this picture in the bottom here, what we do here, we plot compressibility factor versus reduced pressure, this value, okay, reduced pressure, and all lines here like corresponds to fixed reduced temperature 2, 1.5, 1.3, 1.2, 1.11, and different markers corresponds to different gases. Like, well, I don't talk about elephants and students here, they would not fit, but for methane, ethylene, ethane, propane, they're the same. Do you see that they collapse together? So that's why we do it. Please realize. It means that when you do this rescaling, appropriate rescaling, all your substances behaves identically because all ideal gas behaves identically. Do you understand this? That's what we do. That's why we scale it. Again, if I make these plots versus real pressure, if I make this plot versus real pressure, if I make this plot versus real temperature, of course, they will not fit together. They will be distinguished. They will really not collapse. But here, they do. That it is. That's what we are doing. So basically, I put it in the same picture here on this big screen. You will see that if I introduce the scaling for reduced pressure and temperature, all my items will collapse into all these lines. And then you will see from here, so that's what you will be doing next. If you have these diagrams, graphically you can identify, take your pressure and your temperature. Then go to compressibility, then go please to your table and find what is your pressure and what is your temperature. And what is critical pressure and critical temperature. Here you are, right? So for instance, I talk about air. So here is my critical temperature for air, my critical pressure for air. Here, it's the same table A1 that we discussed today. It's a key point for ideal gases. For methane, for instance, here is my critical pressure and critical temperature and critical pressure. Temperature in Kelvin, pressure in megapascals. So you take it, then you take your pressure and temperature, make a scaling, and then what? If you make a scaling, then you will see where you are here for your given pressure and temperature. And then you will find your compressibility factor. And then when you found your compressibility factor, you will say, okay, if your compressibility factor is close to 1, it's ideal gas. If your compressibility factor far away from 1, like say it's here, like say it's 30%, it's not ideal gas. And you may, of course, you may see here what? If your pressure is very small, then your reduced pressure tends to 0. And definitely in the vacuum, all gases are ideal. When your pressure tends to 0, it's ideal gas. But generally speaking, when you deviate from 0, when pressure goes higher, you deviate from here. And basically it becomes non-ideal gas. But later you may see, depends on temperature, points come back. Why they come back here? Because of temperature. Because actually, even if you have high pressure, if your temperature is high, it means that your sensible energy dominates over latent, and still your particles are free. Your particles are free. and then that's why it's still ideal gas. Does it make sense? Okay, just to make you know, I like analogy from the life, just illustration. What we're talking about here, why we did the scaling. Imagine now on my, like I have my desk here, okay? And I put 5 mice, that small mice on my desk. And they are rarefied only 5 mice, so they may look like ideal gas. And let's say I stand up and go a little bit far away from my desk and make a photo of them. So if I make a photo from 10 meters, what I will see? I will have a desk, empty desk, and 5 gray points on it, which are mice. Okay? Now, let's say I have a stadium. And on this stadium, I have 5 elephants, or let's say 5 elephants. And I am on an airplane. And on an airplane from 100 meters of height, I make a photo. What I will see? I will have a place, empty place, with 5 gray points. Do you understand? So what does it mean? Do you agree that 5 mice of my desk observed from 5 meters behave like 5 elephants on a stadium seen from 500 meters? Do you understand this? Yes or no? Great. Do you agree that here I did the same for different gases? I made scaling to make mice and elephants ideal and identical, to make it like points which you see from the distance. Obviously, if I put 5 elephants of my desk, they are not ideal, and I will never see them like a points. And if I put 5 mice on a stadium, I will never see them from airplane, right? Because they will have size, they will differ. Only when I made this rescaling is like this. So the same here. Only when I made this rescaling, my methane, ethane, propane, and water will behave identically when I scale like this. If I plotted real temperatures here and real pressures, all these functions will be crowded, will be redistributed. Do you understand this? Great. So example, I will finish lecture soon, but just very example and your homework, and we may have similar example in your exam, and definitely in your homework number 6 you have it. So how to find the compressibility factor? So for instance, let's say example, let's say I have air at 200 degrees Kelvin and 132 bar, okay? So is it ideal gas or not? How to identify? What I do? 200 Kelvin, 132 bar. I will do the following. First of all, it's air. So I want to find my reduced values. To find reduced values, I will go to my table. And I will go to my table and see for air. What do I have for air? Here what I have. So for my air, I have what is my critical temperature. It's, do you see my screen? It's 132.5 Kelvin. What is my, so it's quite cryogenic. What is my critical pressure? It's about 4 megapascals. And you will see, because this temperature is so cryogenic, in fact, that's why air in the room typically can be treated as ideal gas. But for instance, for water, for H2O, critical temperature is in Kelvin, it's 647 Kelvin, right? It's how much? It's about, what it is? It's like 350 degrees Celsius, it's very hot. So our water vapor, even like boiling water vapor, it's never, almost never behave like ideal gas. Does it make sense? So, okay, so this is my critical pressure and critical temperature. What I do next? I will take my pressure and temperature. Which are 200 and Kelvin and 132 bar, and scale them. So what will be my reduced temperature? My reduced temperature will be 200 over 132 Kelvin. It will be 1.5. Agree? Yes. And what next? Next, I will have what my reduced pressure. It will be 132 bar over 37 bar. Remember, bar is 100 kilopascals, so you can switch it to megapascals. It will be 3.5. So now I know that I have my reduced pressure and I have my reduced temperature. Correct? So now I know, and what else I know? I know that Z is function of these two values. My Z is function of reduced pressure and reduced temperature. So what I will do? I will take this point now. So this is my reduced temperature. And what is my reduced pressure? My reduced pressure is 3.5 and my temperature is here. So here is my point. What is Z? So Z is 0.8. So what is my conclusion from here? What is my conclusion? Yes, it is not ideal gas. It's not 95%. So you cannot use ideal gas law here, right? Because it's not ideal gas. Okay. Does it make sense? This example, does it make sense for you? Is it that, yes, this diagram in the, yes, three, okay, very good, good questions. Yes, this diagram in the appendix, it's on page 15, and 37.7, it was in the table that I see. I'm showing you again. Here is your table, please see. Here is 377 megapascals, which is 37.7 bar. This is your critical pressure. This is your critical temperature. Do you understand? Your real temperature was 200 Kelvin, and what was this? 132 bar. So that's how we schedule it. Okay. Now, yes, in table, if you go to this chart, table 14. Yes, this chart is in table. It's table 14. And you have two diagrams. Typically, you see diagram at the bottom. The diagram at the top is for small reduced pressure from 0 to 1. For big scale, you use this diagram. Yes, it's A15. We call it Nelson-Obert generalized compressibility chart. And why we call it generalized? Because I generalized mice and elephants, right? Because all substances go together to get ideal. Now, what you see here? What is you see here? That if your pressure tends, your reduced pressure tends to 0, everything becomes ideal gas, right? I recall it because here your compressibility factor tends to 1. So definitely, if your reduced pressure is less than like 0.2, something like this, really everything is ideal gas. But then it grows. But what I can show you, that low values of reduced pressure does not necessarily mean that compressibility factor is 1, because you talk also about real pressures. And that's last point I will show. So let's say I will consider the case when reduced pressure is 0.5. So where is reduced pressure is 0.5? It's here, right? It's small value. So if reduced pressure is 0.05, so you are here. That you have ideal gas. But in fact, very small reduced pressure may still be large one. So if my reduced pressure is 0.5, it means that my real pressure is 0.5, 0.5 of my critical pressure. So it will depend on my critical pressure. Where am I? Is it mice or elephant, right? It means that I needed my working table, working desk to absorb mice on big zoom, but I need stadium to absorb elephants. It's different size. For instance, for water vapor, let's see, for water vapor, your critical pressure is very big. It's 22 megapascals. It's 220 atmospheres, very big. It means what? That even that my reduced pressure of 0.5 corresponds still to big value, to 11 bar, 11 atmospheres. Okay? But in contrast, for ammonia, for instance, my critical pressure is twice less. So I have this reduced pressure of 5% at 56 bar. For carbon dioxide, that is what is we breath out, CO2. I will have critical pressure of 73 bar. And my reduced pressure, my small pressure of 0.0 atmosphere will correspond to 3.7 bar. For air, we have in the room, critical, as you already know, your critical pressure is 37 bar. It's big value. It's 37 atmospheres, but your reduced pressure of 0.5 is 1.9 bar. So do you know what we did here? We took a place when water, ammonia, carbon dioxide, and air behave identically. Because if you want to have a cell for elephant, a cell for deer, a cell for rabbit, and a cell for mice, I will have different scales, right? So the same here. It means that for water vapor to behave like ideal gas, you need 11 bar. But for air, you need only 2 bar. That's why air in our room is practically ideal and water not. Do you understand? That air at 2 bar behave like carbon dioxide at 3.7 bar, like ammonia at 5.5 bar, and like water at 11 bar. They all behave identically, but absolute pressures are different. Elephants on a stadium behaves like deers at your backyard and like mice on my desk. Do you understand this? Excellent. I stop at this point. We almost ended chapter 3. We will still talk about ideal gases and real gases on Monday. But at this point, I will stop. I do request you to spend this week on thermodynamics, especially weekend. Please do your homework. And now I will stop sharing my screen and I will be ready to answer questions if you have. I will stop.